My name is Simon Mutch. I am a member of the Melbourne Data Analytics platform at Melbourne University, and we work closely with researchers across all disciplines at the university to try and uplift their data-intensive research. But actually what I'm going to be talking to you about today is from my kind of past life as an astronomer, which I was up until the beginning of this year. And in particular, I'm going to present to you some work that was carried out as part of the Australian Research Council Centre of Excellence for All-sky Astrophysics in 3 dimensions, or ASTRO 3D for short. So I'm going to be talking about HPC simulations of the early universe. I just want to begin by giving a bit of background and a bit of motivation and explain exactly what I mean when I say the early universe. So here I'm talking about a particular period called the epoch of reionization. Not long after the Big Bang, the universe was filled predominantly with neutral hydrogen, but then the first stars and galaxies started to form, and they gave out radiation which was powerful enough to ionize the surrounding neutral hydrogen gas and turn it into ionized hydrogen. And so you got these ionized bubbles surrounding the first stars and galaxies. And then as galaxies grew larger, the bubbles got larger. And as we got more and more galaxies forming, we also started to get more and more bubbles forming until eventually all the bubbles got so big and there were so many of them that they overlapped and the intergalactic medium became fully reionized. And that's somewhere around 1 billion years after the Big Bang. So what makes this particularly cool is that we can actually observe the 21 centimeter emission from neutral hydrogen, which is in the microwave, but it's redshifted to us here on Earth through the cosmic expansion as it travels towards us so that we actually see it in the radio. And so we can directly observe the neutral hydrogen during the epoch of reionization, or at least we hope to be able to in the near future. It's a very difficult problem. But there are lots of large international facilities which are being built and developed specifically to do this. So the reason that we're really interested in studying the epoch of reionization is because it's an amazing opportunity to learn about how the first galaxies formed and evolved. And that's because the statistical properties of the ionized bubbles that I've talked about are sensitive to the physics of galaxy formation, which makes sense because it's the galaxies which are producing the ionizing radiation. But what's really particularly valuable about this is the bubble structure is sensitive to all of the galaxies, not just the relatively bright galaxies that we can directly observe in the early universe. So even with the Hubble Space Telescope and now the James Webb Space Telescope, we're still not seeing the vast majority of galaxies we think exist at these early times. They're simply much too small and faint for us to see even with these telescopes, but they are contributing ionizing radiation, which is in turn contributing to the bubbles. And so if we can have some way to connect the physics of galaxy formation to the statistics of these bubbles, so how many of them are there, how big are they, and their relative size distribution and how that evolves with time, then hopefully we can learn something about the galaxies. So in order to do that, though, we need something that allows us to say, okay, we've measured this reionization signal. What does that mean about galaxy formation? And so typically we use simulations for that. However, there are challenges associated with that. In particular, full hydrodynamic simulations to do this kind of research are extremely computationally expensive. So we're talking tens of millions of CPU hours. And that's because the problem has such large dynamic range. So in particular, if you think about the size of the bubbles towards the end stages of reionization, they're around about 10 million light years or so across. However, we need to be able to study a large number of these bubbles, as well as be able to study the physics of the galaxies which are producing the ionizing photons. So we've got to consider this huge dynamic range from large bubbles all the way down to the galaxy formation physics. And not only that, but as we look further back in time, our knowledge decreases and our constraints become poorer. And that means we need to be able to run a large number of models in order to be able to really probe the free parameters that we want to. So for example, the efficiency of star formation at high in the early universe and things. Now, fortunately, though, we can take advantage of the way the universe is made up, in that if you look at the energy density of the universe, it's predominantly made up of dark energy, so about 70%, about 25% is made up of dark matter, and then you've also got this normal matter making up about 5%. What that means is this normal matter is what we think of as being like you and me, the sun and all these kind of things, but actually it contributes very little to the total energy density. So if we're only thinking about the large scale density distribution, then what that means is we can pretty much ignore normal matter. And that takes away all of the complicated physics of things like shock waves and needing to consider energy conservation and turbulence and things like that. All these complicated parts of the physics that take a lot of computing time. We can ignore them and basically just consider collisionless dark matter. So make it a much simpler n-body gravity only problem, and also dark energy. And we can consider that by just simply scaling our box as the simulation proceeds. What that means is we can split up the problem and essentially pour all of our computational resources into doing a massive high-resolution cosmological volume with just collisionless dark matter, and we only need to consider gravity and nothing else. And then we can, in a later post-processing step, kind of paint on the galaxies to this underlying density distribution. And this is a well-established technique that's been used in astrophysics for decades. And it's the basic methodology that we're doing with the Genesis simulations as part of ASTRO 3D. So in practice, what we do is we run a suite of expensive dark matter only simulations of various sizes and resolutions. And we then identify the dense dark matter structures, which we call dark matter halos. And they're the locations where galaxies will form. And that's because the gravitational potential is deepest there. And so the normal material collapses down into those areas. What we do is we track these halos as they merge and evolve over time to build these nice hierarchical merger trees of how the halos evolve. And this becomes the input for a class of models called semi-analytic galaxy formation models. And we have a model we developed at the University of Melbourne specifically for looking at the early universe called Meraxes. And Meraxes tries to capture all the complicated physics involved in galaxy formation and put it into simple analytic equations that allow us to paint these galaxies onto our underlying dark matter distribution. And then what Meraxes also does is it tries to work out the reionization structure around about galaxies as well. And this was a unique feature of Meraxes when it was first developed. And so this is what we end up with if we just look at one of our simulations and how reionization progresses. And we get these small bubbles forming, and actually what happens inside those is the gas gets heated, and that actually reduces the efficiency of galaxy formation, and so the bubble disappears. And then eventually the galaxies become large enough that they can self-sustain their own ionizing bubbles, get more and more bubbles, they get larger, and eventually they all overlap, and the universe becomes fully reionized. In order to do that, in order to paint on these galaxies and identify the ionized regions, that is much cheaper computational task. So just round about on order of kind of 10 CPU hours. We can even do this in some cases on our laptops if we really need to. And we've poured all our computational resources into doing this n-body simulation. And what that means is then we can really start to explore the unknowns now, because we have a fast model that we can really change all the parameters and see what effect that has. So we can even start to do things like these kind of full Bayesian parameter space explorations. And we can start to do things like make predictions from the model and put uncertainties on them as well, which is extremely valuable being able to do that. Running full MCMC exploration takes many, many model calls. So I just put some kind of rough numbers here, but just to give kind of a very conservative estimate, if we were to do something like a 5-dimensional parameter space, and then that would take something on the order of 50,000 calls, but to be honest, normally it would take about 3 or 4 times that. And if it takes about 200 seconds per model call for kind of a medium resolution reionization run, then that would be 120 days. So of course we can do multiple concurrent instances. So we do that. So say, for example, if we do 12 concurrent instances, we can take that down to something more manageable, like 10 days. However, what we really want to do is to try and get the maximum benefit from our existing computational resources. And this is where we're turning to GPUs. So in particular, we want to try and accelerate our reionization calculations, which are one of the most expensive parts of our Meraxes model. So the way the reionization structure is calculated is using an excursion set formalism. So essentially what that involves is us taking a series of 3D grids and filtering them on successively smaller and smaller scales. and doing some simple calculations then to try and identify on what scales different regions are ionized. Algorithmically, we do this by taking all of our galaxy properties and gridding them up along with the density. So we have things like the size of the galaxies, their mass, their star formation rates, and so on. Then we forward Fourier transform, and Meraxes is parallelized using MPI. And so we use the MPI version of FFTW to do our Fourier transforms. And then we do this simple multiplying the Fourier transform grids by a filter. So that's independent for each cell in our grid. And then we inverse Fourier transform back to real space. And then finally, we do a series of physics calculations on all of our cells in our grid. And again, this is independent. This calculation is independent for each cell. And then we move on to a slightly smaller scale, and we repeat this over and over again. So we do this kind of 30 to 50 times for each snapshot in our simulation. So we did the simplest possible thing, which was to throw these independent calculations onto the GPU. So this multiplied by the filter and then calculate the ionization state for all the cells. And even just doing that simple thing, we were able to get roughly an 8 times speed increase compared to the 1-core situation. However, in reality, we're never really running Meraxes with just 1 core. We're running using 16 or more. And so when we do that, what ends up happening is our improvement is roughly a 3 times speed increase. And for a full run, including everything, including the galaxy formation, that translates to being able to run the model about twice as fast now by moving these things onto the GPU. And so what that means is that we can take these 10 days and move it down to something more manageable, like 4 days. So we can run double the number of model calls, which is really scientifically valuable, allows us to do much more with our existing resources. So there is lots of room for improvement, though, in what we've done so far. In particular, I'm kind of embarrassed to say that we did this using raw CUDA, so we weren't using OpenACC. And what we did is we just wrote these parts here for the GPUs, their own kernels, and then we just have a compile flag that swaps out which version that we're using. And those of you who studied the slides closely will have noticed that we have this CPU step wedged in between our 2 GPU calculations, which means we waste a lot of time on host to device transfers. So in particular, what ends up happening is we have to do all the convolutions on the GPU, transfer everything back to the CPU to do the Fourier transforms, and then transfer everything back onto the GPU again to do the ionization calculation. So a lot of time wasted there. But on the plus side, it required no modification to our CPU version. And also it allows us to run really large grids as well. So we typically run on a system that has 2 GPUs per node. And so once we go above about 720 cubed in grid resolution, we can't fit it all onto the 2 GPUs anyway. Although I will note that now CUFFT has the multi-node FFT capability though. So that's definitely something we want to look into in future. And I also want to point out that we make lots of use of the CUDA multi-processing service, so that when we're running small enough reionization calculations, we try and squeeze as many instances of the model onto a single GPU as possible, again, to just maximize what we can get out of the resources. So as I say, we wrote this in CUDA directly, and that's something I regret. And we're definitely moving in future towards OpenACC instead. And the reason for this is because the code is written by astronomers and it's used predominantly by PhD students and early career researchers. And so development is normally only done to enable new science. We don't spend a lot of time on engineering the model to make it faster or anything unless we really need to in order to explore new science. And what that means is being able to remove any low-level boilerplate and simplify the code is extremely valuable to us for things like onboarding new PhD students. Less code means less opportunities to make mistakes. And in general, it just means we can get to a science result faster. And it also allows us to really rapidly explore the different algorithms and ways we can offload other computations onto the GPU with minimum changes to our code base. So that's basically everything I wanted to say. And I'll leave my conclusions up here and just kind of draw your eye to the last 2 points there. So the first one being yet another demonstration of how we can use GPU acceleration to get important wins without the need to make large algorithmic changes. And of course, OpenACC is really important to allow us to do that. And we're hoping to take advantage of that in future. And also through my role in MDAP, I kind of wanted to point out that I've had the privilege to work with a number of different research domains now. And I'm finding that these kind of optimization and moving things onto the GPU is just becoming increasingly important everywhere. And I think there's lots that we can learn from each other and really great opportunities for collaboration moving forward. Thanks very much for your time.